Welcome to the NMN video tutorials on CSP technologies, Block 6, Unit 10, Necessary Conditions for Performance Measurements. My name is Nicole Janot, and I have been working on CSP technologies at DLR for more than 6 years. My main fields of work are parabolic trough and component performance testing, test evaluation, and performance simulation. This unit covers various aspects of testing conditions and their impact on data evaluation and quality of results. We shall distinguish test operation conditions, disqualifying conditions, operation points and modes, and data evaluation approaches. In the end, I shall summarize the main findings briefly. Necessary conditions to be considered for performance testing can be allocated to three main categories. First of all, system preconditions that are to be fulfilled prior to testing affect the state or the condition of the test collector, loop, or facility. Testing preconditions assure the readiness of the test infrastructure and device under test. And finally, test or operation conditions during testing, like operation modes and test schedules, deal with a good interpretation of the test results. System preconditions for performance testing include the completion of a pressure test of the HTF system for any new or modified installation. Adding new or replacing used HTF implies the need for boiling out in order to purge gases possibly contained. The control and tracking are to be tested to assure the desired operational functions during testing. In case of changes with a potential impact on the geometry of an installation, new tracking offsets must be determined. And for reasons of operational safety, system shutdown and defocusing have to be tested prior to test operation. Fulfilling these system preconditions assures a fully operational system and meeting the required operational safety procedures. As for the start of a new testing campaign, at the beginning of each test, the observation of the following preconditions is essential. The system should be checked thoroughly in terms of full function of components. Are the receiver vacuums intact? Is there damage to the concentrator? Is the cleanliness satisfactory? Furthermore, sensors should be checked in terms of functioning, possible orientation, and the plausibility of the readings. So should the data logger system be checked. If these testing preconditions are met, the system is ready for testing. The most relevant test or operation conditions to be recorded during performance testing with respect to collectors and their operation are the state of the concentrator and the receivers. This comprises the cleanliness, any breakage or loss of vacuum, as well as the record of tracking and operation interventions and peculiarities. As for the heat transfer fluid and the energy balance of the system, the key operational measurements are the mass flow rate, the pressure, and the temperature levels as previously discussed. And for a better understanding of potentially unexpected test results, a full record of ambient conditions is preferable to mere DNI and ambient temperature measurements. There's a number of disqualifying environmental or field conditions if you want to ensure a good validity of measurements. As a general rule of thumb, assuring the representativeness of performance measurements, collector test conditions should agree with regular plant operation rules. This excludes periods of insufficient irradiation and strong winds. Wet receivers should be dried by focusing prior to testing to prevent undesired effects. Likewise, mirror facets that are wet due to dew, frost, or water from cleaning processes are critical. They should be dry and ice-free for testing. Large sun shapes are unfavorable for performance testing because the acceptance angle of a utility-sized parabolic trough collector is usually smaller than that of a regular field per heliometer. Thus, in case of large sun shapes, a pyrheliometer may detect irradiance that cannot be concentrated or used by the system. Evaluating such test data leads to lower values of system efficiency compared to similar test conditions with small sun shapes. Furthermore, a high degree of soiling might not be representative for actual field operation. Especially, irregular soiling patterns are difficult to quantify in terms of average effects in the field. High rates of soiling during testing, constantly decreasing the field's optical potential, imply the need for frequent cleanliness measurements. The test conditions and setup of a performance test produce a certain type of measurement data from which the collector characteristics have to be derived. This way, obtainable collector characteristics are closely linked to the test design. The range of boundary conditions for which the collector or installation is characterized is determined by the measurement range. As for the range of incidence angles, the measurement range depends on the test facility or the field configuration and season, while the achievable temperature levels are determined by the balance of plant or operational strategy of the power block. There are two main philosophies for test design. One is the one of the test facility, a designed or chosen setup with test conditions according to measurement needs. The other one is that of field tests, where as much information as possible is extracted from regular operational data. Both test designs aim at providing the performance information in one way or the other, and reality tends to be a mixture of both. As discussed, the chosen test setup or facility results in a characteristic database. The nature of this database in turn determines the methods required to analyze the data collected. Operation data collected may differ in terms of obtainable operational points. These are characterized in terms of temperature levels, incident angles, irradiation levels, and ambient conditions. The exact ranges of values covered depend on the external influences and the balance of plant. As for test operation, three main modes can be distinguished. During quasi-steady state operation, no operational parameters change with time, while during quasi-dynamic operation they may change within certain bounds. In dynamic operation, however, any transients may occur. Operation modes during testing are characteristic for individual test setups, their controllability, and means of maintaining constant fluid inlet conditions in spite of changing ambient and irradiance conditions. It goes without saying that modeling approaches and data analysis methods need to be adapted to the operation modes for data evaluation. In the following, typical test configurations and resulting test operation conditions will be introduced. Quasi-steady state testing aims at thermodynamic equilibrium, when no quantities change with time. In order to achieve such conditions, after startup, a considerable settling phase is required to even out initial differences and disturbances. During testing, very stable solar irradiance is needed. This severely restricts testing times to perfect solar conditions. Continuous stable testing can only be assured if the useful heat collected by the system under testing is removed completely by the balance of plant. To this end, a powerful balance of plant is required. In addition to removing the heat collected, the balance of plant is to compensate for possible disturbances very rapidly in order to ensure smooth test operation. In turn, steady-state operation facilitates data evaluation as no travel or residence times nor heat capacities have to be considered. The downside is that due to the high level of complexity and associated investments, quasi-steady state testing is only practicable for small units. In contrast to steady-state testing, quasi-dynamic testing describes a testing mode that allows variation of solar irradiance during testing while collector inlet conditions are still kept constant. As a consequence, potential testing periods are broadened by including periods of partial overcast. Good control and sufficient heating and cooling power, however, are still needed to remove the heat collected and to maintain constant inlet conditions in spite of fluctuations of irradiance. Besides, advanced methods of data evaluation are required for quasi-dynamic testing, as the HTF transit times and thermal capacities have to be considered to some extent. With the help of these methods, testing of larger units is manageable in quasi-dynamic testing mode. During dynamic testing, collector or field operation conditions may vary within the normal operation limits. Thus, testing schedules essentially equal regular plant operation, and a power block operated according to its regular schedule balances the solar field. This simplification on the level of testing, on the one hand, results in the need for more sophisticated data evaluation procedures on the other. Due to transients during testing, residence times are relevant and capacity effects of connection piping need to be accounted for. With the help of dynamic testing, tests of large units like collector loops or subfields that can neither be operated according to steady state nor quasi-dynamic testing conditions are possible. The previously discussed operation modes during performance testing can be summarized as follows. Steady-state operation is associated with strict stability bounds and requires precise control and sufficient heating or cooling power. Achieving such perfect conditions is relatively time-consuming and requires a complex and expensive test infrastructure. Quasidynamic testing benefits from considerably broader, allowable variations in terms of irradiance at constant HTF inlet conditions, and thus still requires good control and sufficient heating or cooling power. Dynamic testing corresponds to regular field operation according to respective operation strategies of the solar field and power block. It is thus suitable for extended systems at the expense of a more sophisticated data evaluation. The requirements and characteristics of the individual operation modes determine their suitability for different-sized test installations. For ease of data evaluation, module and collector-scale test facilities are typically operated in steady-state or quasi-dynamic mode. With increasing system size, test operation shifts towards quasi-dynamic and dynamic modes for test loops, and dynamic mode for entire solar fields. For each case, testing at lower levels of dynamics might be possible at distinct short periods of time, but cannot be generally assumed. When evaluating dynamic and quasi-dynamic test data, particular care is required in order to determine the useful heat and relate it to the respective operation point. In this context, transient time considerations and mixing play an important role. There are different approaches towards including transient time effects, some of which are presented in the context of data evaluation in Unit 11 of this block. Fluid element tracing or history divides the HDF flow into subsequent fluid elements and attempts to track their history while passing through the system. Alternatively, transfer functions express overall effects of residence time and smearing of signals representing a system as a parameterized black box. What is essentially required is the performance model relating the useful heat and operation point, preferably expressed as a functional relationship. The parameters of this performance model are obtained by numerical identification, either by means of multilinear regression or optimization, depending on the nature of the performance model. As the system size increases, the evaluation and performance model usually becomes more complex. Distinguishing different contributing effects from one set of test data is an important issue when choosing test conditions. To this end, tests are ideally designed to separate effects as illustrated in the following example. In order to determine the incident angle modifier of an installation, it is preferably set up in east-west orientation or two-axis track, so that different angles of incidence occur in the course of a test day. If the system is then tested with relatively cold HTF, the variation of the optical performance during the day is measured and the peak optical efficiency and IAM can be derived. The thermal efficiency can only be measured in combination with the optical efficiency. To this end, performance is tested with hot HTF at different levels of temperature. For tests carried out at solar noon and an east-west collector orientation, no other effects interfere, whereas for north-south orientation, IAM effects are included in the measured performance. In general, different effects that are a function of the same operation parameter cannot be distinguished in testing and parameter identification. A typical example for such a case is the heat loss of the receiver and the heat loss of the connecting piping. In order to separate these, an additional investigation with more measurement points for temperature would be required. Although during dynamic testing several operation parameters change simultaneously, related model parameters can still be identified by multilinear regression or optimization, if there are adequate variations in the database. Otherwise, parameter correlation can be critical in view of the identification of representative performance parameters. In the course of this unit, we have seen that it is important to match the range of test operation points to the parameter ranges to be identified. Furthermore, Different test setups or installations, such as test collectors, loops, or fields, tend to be associated with different operation modes involving different degrees of dynamics from steady state to fully dynamic operation. In turn, the data analysis needs to be adapted to the operation mode. Conversely, this implies that available means of data evaluation and models determine or even restrict necessary test operation conditions and modes. These thoughts on performance test conditions will be extended in the units 11 and 13 of this block. These deal with data evaluation and parameter identification. This brings us to the end of the lecture on necessary conditions for performance measurements. Thank you very much for your attention.